Carl's going to talk to us about his amazing new business. So over to you, Carl.
Cool. I'm going to try and present my screen and I'm going to try and run Keynote deck just to talk through. And then I will try to stop, do a brief, not exactly live coding demo, but at least hardware demo, and then carry on. Then we'll do Q&A at the end of it. And I'll target being about a 20-minute talk. It might run up a little bit short, to be honest. So more Q&A or however you want to play it. So let's go ahead. Right, first of all, I'm going to try and share my screen. Okay. Can everyone see my screen?
Yep.
Cool. Let's hit the play button. Do you all see a big presentation saying Swift on microcontrollers?
We do.
Fantastic. Spotlighted your video for everyone. All right. Okay. Sounds good. So it's a little bit off the cuff. I've done talks like this before. In fact, this project began as a talk about 5 years ago, around about the same time my daughter began as a little person. And it may be a little rambling, but I'll try and keep it tight, and I'll try and just stick to the basics. So some of this will be things that people know inside out. Some of it will be things that people don't know inside out. So I sort of have to, because I don't know you as an audience, I sort of have to pitch a little bit wider. So hopefully that won't be massively boring. Let's see how we go. So I've entitled it Swift on Microcontrollers. Why is it interesting, relevant, and why is it fun? Which I think is the important things, because immediately if you know microcontrollers, you'll be like, why do you need this? And if you don't know microcontrollers, you'll be like, why do you need this? Which is all fair. So we'll go into it, and hopefully I'll start to outline why I think this is interesting and why I think this is an important new development. So we'll take it on from there. First of all, I'm going to start by talking about what a microcontroller is. So some of you guys are going to know this inside out, but for the people that don't, a microcontroller is basically, I think of it as like a tiny little computer. So it's super small, cheap, low power. These things vary from, a few cents in cost up to more significant values for the sort of high end things that aren't used very often. And there's a real spectrum, and they've been around for quite a bit of time, which I'll go on to on the next slide. But the way to think of it is it's got, as you can see on this picture, it's got the microprocessor, power supply, RAM, a little bit of flash memory with the program on it, oscillator, various things like A to D converters, line drivers, and sometimes other things like CAN bus drivers, all built onto the same chip. And this makes things possible that you wouldn't really expect. So they are all around us. They've been in development since, I think, something like the 1990s. And they're the kind of silent partner to all the other technology that you've got going on. So, for example, here someone's done a teardown of an Apple MagSafe charger. And sure enough, right in the middle of it, one of the most important parts is a microcontroller. And they will be, if I'm sat here in my wife's office, they'll be all around. There'll be like 2 or 3 probably in there. There'll be some over in that printer over there. There'll be some on the TV screen. They are absolutely ubiquitous. And I think people think of them as being, they just control a washing machine or something like that, but that's just not true. Because they're so inexpensive, because there's such a variety of them, they've kind of crept into everything. I'm going to go demo. Yes, we'll go back to that in a second. I think I want to talk a little bit more about what they are. The interesting thing about them is it's a different type of programming, which you're going to see in a minute when I do the demo. And it's much more, you're writing programs that aren't like the sort of standard programs where, you kind of got this routines and UI handling, and maybe you're handling requests coming from a server and stuff like that. You're writing something that's super, super simple. And it's more like you're designing an electronic component. So these things are best thought of as replacing discrete circuitry. So instead of having an oscillator with 555 timers, those kinds of things, you can just drop in a microcontroller. Because they're so cheap, you then write a simple program that does something like turns a signal on, turns a signal off. And it's actually cheaper and simpler to do that than to write, to put in various capacitors and transistors and so on, as you would have done back in the 1970s. So they've sort of revolutionized all kinds of electronics around us, and they're sort of unsung heroes in a way, because a lot of people who program who aren't familiar with this area don't really know much about it. And part of that is because, as I'll get into, the languages until now have been somewhat impenetrable. So let's be brave, and I'll jump in and do a demo using Swift for Arduino and showing you some coding. So we should be back on the screen now. Hopefully you can see me on the video, and you can see the screen here. So you should see Thanet Tech Demo Simple. Is that what everyone's seeing there?
Yeah.
Yeah. So this is the Swift for Arduino IDE. All designed and built by me. I'll get into it in a little bit as to how I got there and where we're at this product. Actually, it's not true to say it's all built by me. It's built by a few people. I'm the sort of primary guy, and I started it off, but it's very much a group project these days. And this shows you how simple a program can be. So I'm going to run this program, upload it. So here we've got hardware. This is a USB cable, which is actually providing power to this, but in fact, you can power this off, batteries, things like that. This is a clone of the board you'd be more familiar with, which is the Arduino Uno. So some of you may have heard of Arduinos. Arduino is essentially a board that just contains a microcontroller and allows you to program it. Arduino came along, I think, 2009, hence I can't say the Italian word for it, but basically one of their first boards was called 2009. And they wanted to, I suppose, democratize or bring out microcontroller programming for lots of people. So they wanted people like artists, students, etc., to be able to do it. They worked off the back of a lot of good work that had been done by other people like the AVR libc guys and the GCC compiler guys. That meant it was possible at that point to create a board that kind of took away a lot of the hard stuff of microcontroller programming, partly the tooling, but also things like voltage instability, etc. So they built a board that basically you could buy for $20. It's relatively expensive for a microcontroller, but it means you just buy it and it kind of works. And they put together an IDE that kind of worked. And this is one of the many, many different types of clones you can get. The microcontroller itself, I believe, but our eyes aren't good enough to see, is this little guy here. If you look on an Arduino Uno, you'll see a big chip, as in a dual DIP chip in a DIP package. That's partly, I think, because they want to allow you to use it as a programmer, but also it just kind of looks a bit more traditional. Nowadays, a lot of the clones just use surface mount devices like that. You've actually got two microcontrollers on there because that one's doing the USB to serial, but that's not an important detail. And these guys, Seed Studios, who make these Grove boards, the nice touch that they've got all these different connectors that you can just plug in these various components. So I just got some of these, I got a load of them in the drawer, and it's quick to put together. So this is basically an LED button. So it's a button with an LED behind it. And I've plugged it in here. That then connects into two pins, pin 3 and pin 4 on the traditional Arduino scheme. And it'll just make my demo an awful lot easier. So you can see the LED is already lit up at this point. And this is the program that's running. I'll show you it uploading, but actually I'm going to be uploading the same program now. So if I do upload, it'll actually build it, upload it via the serial port and via this in here into the directly onto the Atmega 328P microcontroller. And now you've got a program that just, if I press the button, the light goes out. Not very exciting. I've got a slightly more exciting demo that I'll show you in a second. How does this work? Okay, let's do a breakdown on the code. So first of all, we've got this library that we're importing. Now, you may not know Swift. I think that it's probably sort of standardized enough in its syntax that if I talk you through this, you'll understand it. Any of you who've used the Arduino IDE will also understand roughly the sorts of things I'm doing. My initial versions that I've worked for, so let's say versions 1 through 4 of the IDE, or certainly 1 through 3, I was very much emulating what the Arduino IDE was doing, but taking it to a new direction and trying to expand it and bring Swift into the mix. In the newer versions that we're going to and the direction that we as a team are moving towards, and what I'm trying to move us as an organization towards, is kind of starting in our own way, really having completely separate hardware libraries. And I'll talk about that more towards the end. But for now, we've got this library that I call AVR, which you import just like you would in, I don't know, Python or something like that. And that makes available a whole load of functions like pin mode, digital write, which are very familiar if you use the existing Arduino IDE. What this does, if you haven't used the existing Arduino IDE, is you say, for each of these 13 pins that you get on a standard Arduino, they start by default as input pins, a little bit like GPIO pins on the Raspberry Pi. They start as input pins. You can set them to be output pins, which is all that function does. And this is the important way that a microcontroller program is different from any other program that you're going to be using. While true, is not something you would do in a GUI program, because that's an infinite loop and a hang under most circumstances. But that's the point of microcontroller programming. You have total control over the hardware, and that's exactly how it has to be. So you basically write something that's going to run forever, because if it stops at the end here, it's just going to hang. It's not going to do anything useful. So you have to write every bit of the program in there. You've got no operating system, you've got no background tasks. You've got total control over the hardware. And that's quite a different way of programming. It's not what you're normally used to. And it took me quite a while to get used to it. Before I was writing Swift for Arduino, when I was writing C code on the Arduino IDE, it took me a while to get my head around it. And I had to unlearn a lot of the ways I'd been programming when I was writing like database programs, server-side programs, iOS programs, .NET programs when I was in banking, those kinds of things. So what this does is it runs forever, runs all the time, runs fast. And what it's doing is it's reading from pin 4, digital read pin 4, and then it's writing the same value out to pin 3. I've used these constants here, which basically D4 just translates to 4, D3 translates to 3 under the hood, but it just makes it a little bit clearer sometimes what you're actually dealing with. So all this is doing, it turns out I didn't realize this until I played with this button. When you press the button, it actually goes low. So it actually reads pin 4 low, and when you release it, it goes high. So I guess it's held high by a resistor on the back there or something like that, and then you're shorting it to ground by pressing the button. So a very, very simple program, but it shows you how simple and expressive Swift is. Now we're going to something a little bit more interesting. Let's bring up the more complex demo. Now this is where, of course, things could go wrong. So pray to the gods of the demo. When I upload this, I'm going to upload it first, show it, and then I'm going to talk through how it works. So now you'll see the LED is, you might not be able to figure this out, but it's just a little bit dimmer. And when I press it, it goes a little bit brighter. Can you all see that? This is using pulse width modulation. This is how all LED brightening and dimming is done pretty much. The LEDs are turned on and off very rapidly. And generally speaking, what you want to do, and this is what I'm going to get into again when I'm going back to my talk, is you want to have it very reliable and predictable. And that's the essence of microcontroller programming, where it's different. You write a loop that's simple, you don't overcomplicate things so that you know exactly how long things are going to take. It's not so much about how fast things are, it's more about them being absolutely reliable so that they always produce the same signal at the same time. So if we look at the code here, we're first of all setting a few constants. In Swift, let marks a constant and var marks a variable. We don't actually need any of them to be variable because we're not changing any of them. That's not true. It's not a danger shield. It's something else. Let's just call that pins. Live corrections. So I'm using a constant for the LED pin, the button pin. As before, I'm setting the LED pin to be an output. These are my timing constants, mark short, mark long, and space, and we'll see that in a minute. Then what I'm doing is I'm writing the LED high. I'm reading the digital input, the button, to see whether or not it's being pressed. And in this program, I've worked out that low means pressed. So this now is a Boolean value that says, is the button pressed? And then what I'm doing is I'm saying, call a delay function. And these things are very important in microcontroller processing. Delay for the number of milliseconds. If the button's pressed, mark long. If the button's not pressed, mark short. And then I turn the LED off and I call a delay for a space. So what this will do, if you were to draw this on an oscilloscope, if you've got the button pressed, it'll stay on for 10 milliseconds. then it'll go off for 5 milliseconds, then on for 10 milliseconds. And the nice thing you'll get, I didn't have time to hook up a scope or anything like that. But the nice thing you get is you should get a completely reliable waveform. So it's absolutely the right shape, and it's never 11 milliseconds. It's never a 6 millisecond space. It's always exactly right. And that's important because if you're driving something like a motor or industrial machinery, which you might use these to do, then it's critical if you get that right. If there's a bit of jitter in it, then you can have hardware consequences which are relevant. And if the button's not pressed, then it'll be short, so it'll be on for 1 millisecond and off for 5 milliseconds. If the button is pressed, then it'll be on for 10 milliseconds. So that's why it gets brighter when you press it. And one of the things that I also wanted to demonstrate, but the thing that you wouldn't get if you tried to do this on a Raspberry Pi, and I've tried it, is you wouldn't get the reliability. So I did some pulse width modulation using like a simple C program on a Raspberry Pi. And when I run it, most of the time, it's like a weather station that shows a varying brightness depending on how much rain is going to fall on the day. Most of the time it sets about the right value, and occasionally it'll flick up and down, because the Raspberry Pi is doing a whole load of things. It's a computer, it's a small Linux device, and so it's got background processes running and so on. Each of those could come in and take some of your thread time away and make it unstable. And that's why microcontrollers are critical, because you've got full control of the thing. What I suggested I'm going to do here, just to make it a little bit, whoops, let's change this here. So this is the live coding demo. This is where things will typically go wrong. Okay, now let's see how good the webcam is on my laptop. So it actually looks, on my webcam, it looks like it's slightly unstable, but that's actually not true. If I'm looking at it here in real life, it's completely stable. You've got a completely stable pulse, and if I press the button, you've got an absolutely reliable pulse there as well. Unfortunately, the webcam isn't good enough to show that really accurately. That's one of the problems with live coding demos. And the point that I'm trying to show, which actually would probably be better picked up on an oscilloscope, is the fact that you've got this stable waveform with microcontroller programming. I think that will do for the live demo. I think let's go back to the talk, and we'll take it on from there. So if I hit play, will it take where we left off? Should say demo, is that right?
Yeah.
Cool. So why is programming in microcontrollers hard? You kind of got an idea of how it works, and in theory, it's very simple. You're writing programs that would be that you'd be content with on a BBC Micro from 40 years ago, however long it was, writing a very, very simple program. The important thing is predictability. So an awful lot of us nowadays are used to using things like JavaScript, C#, Python, Java, etc. And many of these languages can't give you the predictability guarantees that you need in order to do reliable microcontroller programming. So in order to make something that isn't a toy and something that you could actually build products on, given that these are products that might power, a device like this, and if it goes wrong, then it melts or sets fire to the house, you need to have a language that you can rely on. Generally speaking, as I've said in the bottom point here, all commercial programming today is done C or assembly with some C++. And this is all about the reliability guarantees. And as I've said on the slide, you can forget JavaScript. You can probably forget C#. Definitely forget Python. There are actually MicroPython compilers out there, but in the words of Massimo Banzi, you couldn't build a commercial product out of it, which is what he said when people were talking about it, which I think is accurate. You don't have an operating system, you don't have memory protection. So a lot of the things that you're used to having as a programmer, you just think, when you're a programmer, you think, all right, well, I can throw an assertion. Not really. I can, if my conditions aren't right, if something goes wrong, it'll throw an error and come up on the screen. Well, where's the screen on here? There isn't a screen. So it's a very different way of thinking about programming, and it can be disorienting for people. So that's why it can be hard when you're not used to it. And I mean, of course, there are, a load of people who do it professionally, and there are hobbyists who are used to it. But I think for a lot of people, if you take the majority of programmers, when they come to the platform, they're not really sure how it works, and they're not really sure. They just get disoriented, which I did. So there we go. Now I'm going to talk a little bit about Swift, which is the language that I've chosen to use. And I'll go into the background a little bit towards the end of the talk, as to how I got to where I am. Matt said it would be interesting to say, so go a little bit of a potted history as to how we got there. Swift, some of you may know this, some of you won't. It's primarily seen as Apple's language, which isn't really accurate, but it's sort of reasonable. It was started by the creator of Clang, so probably more of you will have heard of Clang. So Clang is, I think, generally considered the competitor compiler next to GCC. So GCC is the sort of most standard C and C++, and actually lots of other languages, Fortran, etc., compiler that is used all over the place. Like it compiles, for instance, Linux is compiled in GCC. Clang is a competitor, and it's a very good product, and it's very widely used commercially. There's all kinds of companies who are interested in it. The partner of Clang and the thing that came before Clang is LLVM. So these were both created by the same guy, Chris Latner. And LLVM it's the way to think of it, I think, is components to build compilers. So it stands for low level virtual machine. The idea is that you have a language, whichever your front end is. So Rust, you may have heard of. Ruby, I believe, is another one. Kotlin, various other languages like this. All of these front-end languages, C, of course, via Clang, Swift, and various other languages, they all compile down to this intermediate representation, which is LLVM intermediate representation, or some people call it bitcode on the Apple platforms, those kinds of things, which is a sort of a middle ground. So it's a lot like other intermediate languages that you might have heard of, like IL on .NET or bytecode on Java. So there's similarities and there's differences. It's more like a compiler intermediate. And then from there onwards, there's all of these optimizers that can then operate in the same way. So you can have all of these different optimizers. Doesn't matter what your front-end language is, the same optimizers work on all these different things, which gives you all of this kind of extra power that you can put to use in all these different languages. Then at the end of it, there's something that produces machine code for your platform. So you can produce machine code for MIPS, ARM, AVR, Intel, of course. Lots of different processors, and that's the sort of the benefit and the sort of the underlying thing behind Clang. One of the reasons why people like it. Chris Latner, at the same time that he was building Clang and producing a C++ compiler, he was getting increasingly frustrated with C++ and all of the issues that it has. The kind of the fact that it can do so, it's been around for so long, it's got so many different alternatives, it's so hard to be 100% sure that you've got all the bits, it's hard to be an expert in it. And of course, all the things like the preprocessors and all the flexibility that make it difficult for you to reason over the languages in some ways or to do certain optimizations. So he kind of came up with this idea of building his own language from scratch. I think they called it Shine in the original days or something like that. They had some crazy name for it. And then much later on, they came up with the name Swift just before launch. He convinced Apple to back it, and Apple made it their language in 2014, released it with this big fanfare. And so for 8 years, it's been the primary language that Apple are pushing. And they open sourced it 2 years later. So companies like Google and IBM and various other smaller companies started to take an interest at that point. It's C type syntax, modern language with things like generics, protocols, composability, automatic memory management, type inference, pattern matching, and dynamic features like virtual methods, good string handling. And it's got a very comprehensive standard library, which is very useful for any kind of modern language. And the thing that I've touched on in the middle of the slide there is it's built around predictability and safety in a similar way to Rust, but a slightly different approach from it. And for example, when you're dealing with integers, there are these whole classes of problems to do with integers, changing one type of integer to another type of integer, and C just kind of does it for you and makes a guess and often guesses wrong. And that's just like this source of huge numbers of issues and bugs and various other things like that in C, often security weaknesses, with defined parameters, null pointers, etc. Swift takes away a lot of that unpredictability. And it's very much built around making something that's a predictable language. So they're also still trying to get C-like performance, and they pretty much achieve it. So a Swift program would typically be about as good as your average C program. Certainly your average C program written by someone who's not Linus Torvalds or just a normal programmer. It produces, I've seen this myself, when you write Swift programs, it produces efficient assembly language at the end. It's slightly dependent on what your LLVM backend is. If they're not massively well written, like for example the AVR, which are the chips behind this, the backend is still a little bit in its infancy. So it's recently, about 2 years ago, become a mainstream backend in LLVM and supported to that level, but it's still got some work to go. But generally speaking, it produces efficient code. But at the same time, it does things like checks your array bounds. So if you go outside your array bounds, it still crashes, but it crashes in a defined way. If you try to access pointers, null pointers, there isn't really exactly the same thing. There's these optionals, but if you try and access them and try and force unwrap them, then it will crash in a defined way. And this is really important with things like embedded programming, because you're avoiding whole classes of security bugs and various other hard to find bugs. It's all about finding the things much earlier, because these guardrails kind of fairly efficiently stop you from producing programs that are dangerous and unpredictable, which is the kind of key thing about it. The community is very large, passionate, not large as in as big as Java or Python, no way, but it's pretty big compared to a lot of other languages. You'll see it in the TOB index and those kinds of things. Very much dominated, of course, by iPhone developers and to a lesser extent Mac developers. There are a few server-side guys. I think it's been interesting for me. I do Swift as my day job, so it's sort of a natural thing to reach out to. I'm increasingly starting to realize that it is a somewhat iOS dominated sphere. So I think later on, we're all talking about what other languages we can bring into this tooling. But interesting. It's currently on version 5.5, version 6 coming soon. Now, Swift for Arduino. Swift claims to want to be a multi-purpose language from UI down to system programming. However, so that's their basis. And because it does things like, for example, memory management, is done using essentially things like smart pointers. So it does reference counting, but it builds all of the kind of retain release code in there automatically for you efficiently. So it doesn't do things like garbage collection, which can produce unpredictable behavior in embedded environments, certainly things like microcontrollers. So it has got a lot of the components there, but in my experience, the bare metal end really hasn't had a great deal of love. So it's slowly improving. I put in various patches to the Swift compiler. At first, it didn't work with things like 32-bit at all. So you couldn't have a 16-bit pointers. You had to have at least a 32-bit pointer, which is not really acceptable in, for example, in this microcontroller, it's an 8-bit data bus and a 16-bit address bus. So it's not, it needs some tweaking to get things working. They are getting better, definitely. And me and my team have got a very good understanding of where the rough edges are. The first prototype that I wrote basically took LLVM-IR from a Mac type output and cross-compiled it to AVR assembly, and it was a little bit flaky. So I came up with this idea. The first concept I came with about 5 years ago, and then I just kind of tinkered around until I had something that I could demo. Demoed it at a talk at Swift London, very well received. People liked it, wanted to have a go, and wanted to help, which was the important thing. So at that point, I started to get people involved, sort of helping out, volunteering, and started to think about productizing it. It took about 18 months to get something out that was kind of a product. It was like version 1. And I've been selling it at first, and now it's a little bit more complicated. It's kind of free, but it's a bit different. For I don't know how many years that is since then, sort of about 4 years, 3 years, something like that. The current version 4.9.2, has a customized standard library, custom Swift front ends, endless bug fixes, and our own hardware libraries. And it's currently being used to build, for example, one commercial hard real-time microcontroller-based product. My team in America that I'm working with are helping to build a synthesizer. So this kind of amazing, partially analog, partially digital synthesizer with all of the code written on Atmega 328P microcontrollers written in Swift for Arduino. I'm not allowed to tell too much about it because it's under NDA until the guys sold it. But it's the important point is this can be used to build commercial products, even though it's a language that is much more familiar to people who are used to modern programming languages. So a little bit of a chat about the future before we go to Q&A. A lot of these won't mean anything to any of you, but for me and my team, we're quite excited about it. We all kind of, a lot of us effectively volunteer. So I was charging for the IDE, but essentially, you know, 1 or 2 people were buying it a month. Seemed a bit unnecessary, really. So now it's essentially an honesty box system. You can download the IDE for free and use it for non-commercial use, unsupported. If you want support or you want to do commercial use, then I ask you to pay a license. And we'll take that as a model going forward because we're trying to make an investable business. And I spent the last sort of 9 or 10 months trying to approach investors, which was an interesting task. But we all sort of come and go with it. So the other core team members, Axel, Paul, and Mark, and Bill and Craig, who are our consultants, they come and go as they've got time, and sometimes they get paid work out of it, like the commercial product that I was talking about. The things that we're working towards when we get in that direction, when we've got time to do it. Mark's pet project is called EDSL. So this is domain specific language for embedded programming. And it's he's got to talk about it on YouTube, so I can mention YouTube channels at the end. The one thing I haven't done is given links, so I can give Matt a page of links at the end of it. But basically, we've got a YouTube channel where I talk about some demos for Swift for Arduino, and it's got Mark to talk about EDSL. It's really quite an amazing product, actually. It's basically like if you imagine writing microcontroller programs by a declarative syntax, saying essentially, if this button's on, then that action will happen, those kinds of things. But it's a really exciting project, and it'll kind of dovetail across. We're starting to think of this kind of spectrum of things. So we'll have the core low-level stuff where you're programming 8-bit microcontrollers, things like that, maybe 4-bit microcontrollers, you know, all these kind of low-level things. You've got that core language, but we'll also have higher levels when you can do things like have reference types, more advanced memory management, domain-specific languages, things like that. The next big change for us is going to be this hardware abstraction layer, where we're going to move away from this sort of Arduino-like thing to generalized hardware abstractions that will work across AVR microcontrollers, certainly, and across a whole load of microcontrollers. And there's a lot of kind of interesting stuff. And then the next 2 processor architectures that we want to support is ARM and RISC-V, which some of you guys will have heard of. I actually was in touch with Sci-Fi, who are a company based out of California who make RISC-V reference architecture based on that. Chris Latner was working there for a little while. So I reached out to him and had a chat to him for a little bit, which is interesting. And he put me in touch with the Sci-Fi guys. So I'm keen to do those things as ever because it doesn't pay the bills and because I haven't been able to get investment up to this point. It really is when I can fit it in. But yeah, it's, you know, that's the way things are. And I just want to finish with a thanks for listening to me ramble on. I wish it could be a little bit more polished, but you know, I never quite know which way I'm going to go on that.
Carl, do you have a hardware simulator as part of your IDE?
Yeah. So I'm using the SimAVR simulator, which can simulate a variety of AVR chips. And you can, is it worth demonstrating? No, it's not really worth demonstrating, to be honest. I can just bring up the window. So am I not sharing at the moment? I'll do a quick share screen, just as you can see. So you've got down here, I haven't got any serial output, but if I wrote something in here and I didn't have a board plugged in, so if I unplug my board for a second, then it switches to simulator. Down here, when I write something that produces output, it would come out here in the serial monitor, basically for the simulator. When I plug the board back in, it'll go back to the. This is now showing the serial output from the board. Let's stop sharing again. So yes, in essence, it's interesting actually that I really thought that would be something people would use a lot and would be important for people. No one but me uses it, funnily enough. So I think there's a couple of rough edges on it, which are just my not programming things quite well enough in the IDE. It's a Mac app, and I think there's a couple of things that I could maybe improve a little bit on that just to make it a little bit more reliable. And then I'm trying to get a debugger working so that you'll be able to do, kind of full breakpoints, etc. if you run it in a simulator. And I think that would make people more tempted to use the simulator so that you could debug your programs that way. But yeah, ultimately, this is a hardware business and people run it on hardware.
And I'm quite interested in, do you use Unos in projects or anything like that? How did you get into the embedded world?
It's funny. It's funny. So the funny thing is that I definitely used to, but now I spend my time writing compilers. So the nice thing is I've got teams of people I work with who are using it and keep saying, oh, this is giving me feedback, etc. I was, brief history of me, I've been writing programs for some time. I think my first commercial stuff was Fortran on DEX, and I did Oracle and sort of a lot of corporate stuff like that, and then got into Microsoft, and then eventually decided Microsoft in banking was fine, but it wasn't for me, and I wanted to do something more exciting and sexy and new, which at the time in 2008 was iPhone. So I've been an iPhone developer professionally about 11 years, and around the early days of that, I started to get, I can't really remember why, but I started to get interested in Arduino. Someone mentioned it, said you should try this Arduino thing, and that would have been about 2012, I should think. And I'd always been sort of interested in electronics and hobby stuff when I was young, and hooked, like to hook stuff up to my BBC Micro when I was a kid. And I think this made it appeal to me. So I'd sort of thought, oh, it'd be interesting to do things like, control some of my lights at home with that. And it was great fun. I got an Arduino and I started playing with it. And I had the experience, which I think any of you who've had Arduino Unos will have, which is where I started writing stuff, and it was fine when I was downloading demos and fine when I was doing the demo projects, follow this step, follow that step, etc. The minute I started to step off the path, as it were, to add an extra pin, it was okay to begin with, and suddenly it would break. And I've written, for example, I wrote this a dimmer switch control. So I had it doesn't really work with LED lights, but I had like a light bulb in the corner, like a traditional light bulb, and I got this device that I bought by accident, literally an internet purchase, which basically could turn the light on and off and detected zero crossing. So if you've ever done a dimmer switch in code, you basically detect the zero crossing, then you wait a fixed period of time, and then you turn your triac on, and then that's, the longer you wait, the more light you get, the less you wait, the less light you get, that kind of thing. Or you can do it the other way around and wait until you turn it on. Yes, in fact, actually, that's the way you have to. Correction, it's been a while since I wrote this project. So I wrote that, got it working, obviously wanted to hook up an iPhone to it. And I made a sort of primitive HTTP server, super simple, on the Pi, on the Arduino Uno. And just got to respond to a couple of very basic commands, and I'm just used to things like that working, and it would sort of work, and then after a while it would look like it'd be in the corner of the room, and my wife would say that it's gone wrong again, and it would be flickering. So I could control it with my phone, and I could make it brighter and dim, and I was like, this is great, it's cool, look at this thing I built. And then once a day or twice a day, it would just start flickering on and off like that and go crazy. And eventually I realized that it was like a 1 byte buffer overrun. So every time a network packet came in on the Ethernet, it would eat up 1 more byte and kind of inch through. So depending on how much network traffic there was in the day, eventually that 1 byte buffer overrun would hit something important and the whole program would destabilize. And that's the sort of, and I don't even know for 100% certain that's what was going on, but that's the kind of thing that I experienced, that plus all the problems with integers, plus, buffer overruns on strings and all those kinds of things. That it just led to a lot of years of frustration, really. And I didn't start off thinking I'm going to write a new language to fix this. I wrote the first prototypes of Swift for Arduino because I thought it was cool. And I thought this will make a fun demo, and I wanted to come up with a nice talk for Swift London. And after it was well received, I started to think, maybe this is something that people would want to use. And I started to think, I'll make something of it. And then eventually, after a year or so, I thought, well, this is something that I'd like to make a company of and make it something, that grows somewhere. And I knew that would then mean that it had to have something closed source in parts and have intellectual property, etc. So I kind of went down that route, which is the route that I followed until relatively recently. And I think we're still very much thinking about how we can monetize and turn this into a company, which we've paused on since about February, because we've all got our own projects. So we're kind of just pausing that until a little bit later this year. I don't have an answer really. It's talking to investors. It's just hard to explain something like this to people who are used to the idea of, so is it Bitcoin? No. Oh, it's not. Oh, right. Okay. So is it a health tech thing? No, it's not. Okay. What is a compiler? Why do I need? I don't know. It doesn't sound for me. So it's, and they're not wrong in a way. What is the ultimate total market size? How do you, et cetera, et cetera. But it sort of gets away from, when you come up with a new technology, you come up with something that you think can really change the way people do things. So allow loads of programmers to write microcontroller programs. I've been actually much more sold on this by the people who joined the project, the people who came in, started to use it and were enthusiastic and said, I've been looking for something like this for such a long time. Like Mark, my CTO, he was like, I kept wanting to find something that would help me write microcontroller programs. He's more experienced than I am. It started to grow on me as an idea that this is actually something that really could be useful and could change the way that people build things. But of course, to sell that vision into, the hard-nosed reality of someone who wants to say, well, when am I going to get my money back is tricky. So we're still trying to figure out how to square that circle. And I don't have an answer on it. We don't know really.
Mm. Yeah, I like your focus on the predictability aspect of these embedded things as a key difference from laptops, etc. I've never heard them described in that way, but it is fundamental, as you say.
Yeah.
It's an important part of it.
Yeah, and that's why Swift is a good language, because it is based on predictability in a way, because in a way it is a language that was built for an embedded device, because an iPhone is sort of an embedded device. It has less so now, but certainly in the early days, it had real constraints on what you could do with the battery and the CPU. I'm working as a consultant at the moment for a company out in Paris, and they've just released an iPhone app update that for me, it's burning the battery and it's using up loads of CPU. So we are getting to the stage now where people write programs like that. They would write a server-side program. It's a cool app, but it's much more focused on, the kind of usability and features, and less on the hardware and, kind of this parsimonious program writing that used to be so important in the early days of iPhone development, which attracted me actually. So it's sort of interesting, but the language kind of started from there, and it's got its roots in things like Objective-C, which again is very much a language that's C based, was created by Next Computers, the guys who Tim Berners-Lee wrote the the World Wide Web on one of those, and they're pretty famous machines. So it has got kind of performance chops and language chops. But yeah, it's kind of interesting that this is really the unique selling point. So when you go to sell this to someone who really doesn't know about programming, you've got a double whammy, because it's hard enough to explain to guys like yourself who are technical people and who are, probably most of you have got experience in programming, explaining to you why it's so important to have something that runs real time, to have tooling and languages and libraries that are carefully thought out in that regard. If you want to sell it to embedded people, where they're like, well, we've been doing this for years, we don't need your tools. So it is a bit of a tricky thing to sell into even the programming market, to then go out there to talk to commercial business people and to say why it's important. I mean, how do people sell the wheel in the first place? Something like antibiotics sells itself. Like when someone came up with that idea, it's like, yeah, obviously this is a great idea. But when you come up with a new technology or a new approach, it can be difficult to persuade people. And I think a lot of that is persuading people to give something a try, because, we're all got projects that we want to do. We're all short of time, and we're all sitting there thinking, okay, well, if I spend my time on this, then I can't go out and learn about machine learning and so on. So what do I spend my time doing? So it's, it's an interesting one, really. I love it. So it's easy for me.